Imagine a world where signals travel faster than light. What would happen to cause and effect? Welcome and thank you for joining. In this presentation, we will explore fascinating and controversial idea in modern physics, the tachyon, a hypothetical particle that moves faster than light, and its implications for causality within special relativity. Tachyons were proposed as particles that never go slower than the speed of light, while bradyons, like electrons, have real positive rest mass. Tachyons would require an imaginary mass, something not found in physical particles as we know them. They always remain in the superluminal regime. Bradyons, luxons, and tachyons form three theoretical classes of particles based on their speed. The laws of special relativity strictly prevent any particle from crossing the light speed threshold in either direction. This creates a kind of causal boundary between different types of particles. If you could send a signal using a tachyon, it would arrive faster than light. But relativity tells us that different observers might disagree on the order of events. One observer may see the effect occurring before the cause, leading to troubling paradoxes. Let us now turn to one of the most well-known consequences of tachyons, a paradox first discussed by Richard Tolman over a century ago. It is called Tolman's paradox, and it plays a central role in discussions of causality. It led to the concept of a tachyonic antitelephone, a thought experiment involving two observers who use faster than light particles to send messages into the past. Of course, such a device has never been built, and there is no experimental evidence that tachyons even exist, but the conceptual consequences are profound. This is the heart of the tachyonic paradox. Suppose person A agrees to send a message only if they don't receive one, but person B sends a reply only if they receive a message from A. Now the contradiction appears. A sends a message if and only if they don't send it. This creates a logical loop, a self-contradictory condition where the message exists only if it doesn't. It's not just strange, it's logically impossible. Now let us turn to a technical discussion of Tolman's paradox. In 1917, Richard Tolman proposed a thought experiment that shows how faster than light particles, if they exist, could be used to send messages into the past. This idea appears in his book, The Theory of Relativity of Motion. It is one of the earliest and clearest discussions of how tachyons might not just violate causality in principle, but allow you to build a device that communicates backwards in time. We will now analyze this paradox mathematically. Suppose a tachyon signal is sent from event A to B. In the original inertial frame, as time difference is simple, distance over speed. But when we look from a moving frame S prime, the picture changes. Let's now examine how special relativity transforms time between different observers. Imagine two events. The first is when a tachyonic signal is sent, and the second is when it is received. We are observing this from a reference frame, which we will call frame S, where both events take place at different locations along a line, like the x-axis. Now we calculate the time difference between these two events in frame S by dividing the distance between them by the speed of the signal. In this case, a speed faster than light. This gives us a positive time interval. The signal is sent, then received. But now consider another observer who is moving at a constant velocity relative to the first. That observer is in what we will call frame S prime. According to special relativity, time in S prime isn't the same as time in S. It depends not only on what time the events happen, but also on where they happen in space. That is because in special relativity, time and space are intertwined. To find the time between the two events in this moving frame, we apply what is known as the Lorentz transformations. Without going into the equation, the result depends on two things. First, the relative velocity between the two observers, and second, the speed of the signal. If the signal is fast enough, faster than light, and the observers are moving fast enough relative to each other, the transformed time interval in the moving frame can actually come out negative. That means the order of events gets reversed. The observer in the moving frame sees the signal arrive before it was sent. In that frame, the effect happens before the cause. That's the paradox we are heading toward. Here is the heart of the paradox. If the signal travels fast enough, and if the observer is moving quickly enough in the right direction, the calculation from the previous slide shows that the time difference in the moving frame becomes negative. In plain terms, that means the signal appears to be received before it was sent. This is not just a weird curiosity. It is a deep problem. In this moving frame, the person at the receiving end would see the signal arrive, and then later, according to their clock, the sender would decide to send it. In other words, the effect comes before the cause. This completely breaks the normal structure of cause and effect that our physical theories depend on. If tachyons could be used to sense signals, different observers would disagree about which event caused the other. One person might see a message being sent, while another would see it arriving first, even before the decision to send it was made. This is a violation of causality, which is the backbone of physical reasoning. It would allow for scenarios where people could respond to messages they haven't yet received or send information into their own past. And that is the stuff of paradoxes and science fiction. That is why, despite the mathematical possibility of tachyons, most physicists reject the idea that they could ever interact with normal matter or carry usable information, because they would undermine the very notion of a consistent timeline. Special relativity sets the speed of light as the upper limit for causal influence. If a signal exceeds that speed, then in some frames, the effect can happen before the cause. Tachyons, being faster than light particles, create exactly this kind of paradox. They threaten the consistency of cause and effect, which is central to how physics works. That is why their theoretical existence is so controversial, not because relativity forbids them outright, but because they undermine the logical structure of the theory. Einstein's theory of special relativity permits what we might call forward time travel. For example, when someone moves close to the speed of light and experiences time dilation and the twin paradox, but it strongly disfavors any form of backward time travel, which would allow one to alter the past. Tachyons, if real, would lead directly to that kind of contradiction. This is one reason physicists remain skeptical. Even in 1917, Tolman saw the problem. He acknowledged that while this type of causality reversal might not be logically impossible, it is so strange, so alien to the way the universe seems to work, that it strongly suggests nature doesn't allow anything to send causal influences faster than light. Decades later, in the 1960s, physicists re-examined the issue. They noted that relativity prohibits crossing the light speed barrier. For example, you can't take a proton and push it past the speed of light, but perhaps there is a class of particles, tachyons, that always travel faster than light and never need to cross that barrier. Just as photons are born moving at light speed, perhaps tachyons are born moving faster than light. Still, the problem of causality remains. Imagine another version. Observer A sends a pulse of particles at infinite speed to observer B, who is receding at constant velocity. Upon receiving the pulse, B sends back an immediate reply, also at infinite speed. From their perspective, the reply reaches A before they sent the original signal. A has received a response to a message they haven't yet sent. Once again, we have a closed causal loop, a logical cycle in which cause and effect reverse their roles. This famous limerick, often cited in physics discussions, captures the spirit of the paradox humorously. If you go faster than light, you can in principle return before you left. It's a playful take on a very serious problem. There was a young lady named Bright, whose speed was far faster than light. She went out one day in a relative way and returned the previous night. In relativity, when a particle exceeds the speed of light, different observers can disagree on whether it's moving forward or backward in time. In some frames, its timeline runs in reverse. This leads to the possibility of a closed time-like loop, where information returns to its point of origin before it was ever sent. This violates causality at its core and suggests that tachyons, if they exist, cannot carry usable information. Thank you for watching this presentation.